seen the vector spaces, subspaces, and various new vector spaces that could be obtained using the well-known examples of vector spaces. Now, we would like to see some relationships between the elements and how do they behave. So, first of all, let us define a linear combination for elements in a vector space V over F. So, let us say. So, let us take that V over F be a vector space, and let us take elements. So, say V1, V2, Vn. The elements say V1, V2, and so on. Say Vn in V, and any expression of this form. An expression of the form, let us take alpha 1 V1, alpha 2 V2 plus 1 plus alpha n Vn. Now this expression has alpha is from F and Vj's from V, and therefore this becomes an element of V. This is called a linear combination of the vectors V1, V2, Vn in V over F. Now we can collect all of these elements. So suppose we have a subset here of the vector space V, and we collect all the linear combinations. Then we say that this is the linear span of S in V. So let us take that S be a subset of the vector space V over F, and suppose this is not empty. Then the set LS denotes a set of all possible linear combinations. Of vectors from S over F. So what does LS consist of? So LS consists of elements of the form. To save space, we can use the notation of the summation, say I is equal to 1 to say n alpha I Vi, where these Vi's are from S and alpha J's are from F. This n is not fixed. This is finite but not fixed. So all possible linear combinations of vectors, say Vi is from S over F, is called the linear span of S in V over F. So this is LS is called the linear span of S in V over F. And naturally, therefore, LS is a subset here of V. So LS is a subset here of V. And in fact, you can use the fact that the sum of two linear combinations is also a linear combination. And if you multiply by alpha, a linear combination, it is still remains a linear combination. And therefore, this set LS is closed with respect to addition as well as with respect to the scalar multiplication. In short, it makes that this LS is a subspace. So, in fact, LS is a subspace. Now, note that for subset we use the containment as it is, and for subspace we use this triangle here. So, this is subspace of the vector space V over F. Now, we can also see that if there are subsets and corresponding linear spans of these subsets, depending on then them that S is contained in T, what will happen to LS and LT. So this is an easy observation which you can prove yourself. So if you have, let us say that S is a subset of T and S is non-empty. Henceforth, whenever we talk about the linear span of a subset S of V, so we shall conventionally assume that S is not empty. So if S is a subset here of T, correspondingly, then correspondingly the vector space LS will be contained in the corresponding linear space of T. Naturally, when this is contained here, so you can say that this is also a subspace of LT. So if you want, you can here, instead of taking just this, you can say that this is a linear space. And are subspaces of V. You can also see about the union, say for example, the union of S and T, that also is a subset here of V, and the linear span of this will be a subspace here. And you can also see that one subspace is LS, another subspace is LT. The relationship between these three is as follows: that LS is a subspace, LT is a subspace, and therefore their sum is also a subspace of V. So all of them are subspaces of V. And here actually that not only the L of S union T is contained here, in fact these two are equal as subspaces. So the linear span of S union T is a subspace which is same as the sum of the linear spans of S and T. And you can also see that if you have a non-empty subset S, you get a subspace, say LS, which is the linear span of S. Ultimately, a subspace is also a subset of V, and therefore, if you take once again the linear span of this, then this is the linear span of S. So it remains so same as the linear span of S. Now, something which is important here is that we can define that because they are subspaces, but it also might happen for some subset S of V that its the linear span is actually whole of V. So the if S is a subset of the vector space V such that S is finite and the linear span of S in V is the whole of V, and this is a vector space. That means the linear span of S is the whole of the vector space V. So there is some finite set of vectors in V such that their linear span is whole of V. In that case, we call this V to be a finite dimensional vector space. Then V is said to be a finite dimensional vector space over the field F. We can have some examples. Let us take the example, say R over R. First of all, so for example, the vector space V R over R is a vector space, and if you take say for example S to be the set which consists of just one. Now what we know is that any real number, since any real number here, so is V in R or R is a real number, and this can be written as here you can take that V is equal to your alpha, and this is your V1, where alpha is V and V1 is this one. So this is a linear combination of the vector, namely the real number 1. This alpha here treated as the scalar is a real number, and therefore is a linear combination. And so what we get here is that we have a finite subset S, namely the singleton one, which consists of just one element, and it has the property also that its linear span is, so the linear span of this S is whole of V. So what we get here is that V is finite dimensional. As V is finite dimensional. So for that matter, let us take the case when V is Fn over F. Where F is a field and Fn is denote where F is a field and Fn denotes the set of all n tuples. Let us take this is say your x1, x2 and say xn. Each xi is from F. Then we know that Fn over F is a vector space over F for every field F and for every positive integer n, where the addition is defined coordinate wise and a scalar multiple of an n tuple x1, x2, xn is the n tuple, where each coordinate xi is multiplied by alpha. So alpha times this n tuple is the n tuple alpha x1 times alpha x2 and so on alpha xn. So this becomes a vector space with respect to this addition and a scalar multiplication. And for this, let us take that as to be the set which consists of say V1. The vector V1 in V means is an n tuple. So take this n tuple as first coordinate is 1 and all the remaining are zeros, and V2 means the first coordinate is 0, second is 1 and all the remaining are zeros, and so on. The Vn is actually the n tuple where the first n minus 1 coordinates are 0 and the last one is your 1. Now you can easily see that this is a subset here in V. And in fact, you can also prove that the linear span of this is whole of V. For any vector V in V, this is basically is an n tuple. So means there exists say alpha 1, alpha 2, alpha n such that V is equal to alpha 1, alpha 2 and alpha n, where each alpha I are from F. We can write here that this is the same as V is equal to alpha 1, and this is you can see that this is the way we have defined the sum coordinate wise and scalar multiplication like this. So this in turn is the same thing to say that this is the linear combination of V1, V2, Vn. So every vector in V can be written as a linear combination of the vectors V1, V2, Vn from S. So that makes this linear span of S as whole of V, and since S is finite, so what we get is that this is finite dimensional. Hence V over F is finite dimensional. So like that, you can have many such examples. You can also take, for example, one more example, let us take. So let us take V to be the set of polynomials fx. Polynomial means it is an expression of the form say a naught plus a1x and say an x power n an x, such that you can take that these AIs they come from F, a field F, and you can also take that an is not zero. So this consists of polynomials in X or a field say F, and say an is not zero. So this means, but prior to that they can be zero. So if you take this, this is the set of all polynomials of degree n. But in that case, this doesn't become a vector space. So this is not a vector space. Because if you take fx and gx to be the same polynomial and you take the difference, then this is the zero polynomial. So the set of all polynomials of degree exactly equal to n do not form a vector space. However, if you do not restrict this, then let us take this say Vn, all polynomials here. So AIXI, if you want, you can write like this also. Let us take this say M कर देता हूँ मैं इसको. So M. AIs are from F. M is fixed. M is fixed. So this is the set of all polynomials in X over F of degree at most M. Then this is a vector space. then Vm is a vector space of V, which is the vector space of all polynomials. Fx is to denote the set of all polynomials. So this is the vector space all polynomials over f in x. Now for Vm, if you just to take the set say S, let us take the set S to be consisting of 1 and say x square xm, because it may also have the power xm. Now this is a set consisting of these m plus 1 polynomials. So this is a subset here of V, and can also note that every fx for every fx in Vm, we can write this fx as a linear combination. So alpha I xi. So this is 0 to m or some scalars. Let us take alpha 0, alpha 1, alpha m from f. So any vector in Vm, which is a polynomial in x of degree at most m, can be seen as a linear combination of 1 x, x square and x power m. And therefore, what we get is that the linear span of S or M is actually Vm. Once it is the whole of the vector space Vm, then we know that Vm is a finite dimensional vector space. Over F. So like that, there are plenty of examples of finite dimensional vector spaces. We now talk about the relationship that it may have within the elements. So what we call that when the vectors are linearly dependent. So vectors are linearly independent means what? So let us take V over F be a vector space, and the vectors say V1, V2, and say Vn in V are said to be linearly dependent over F, the field F, if there exist scalars, say alpha 1, alpha 2, alpha n in F, such that the linear combination say alpha 1 V1 plus alpha 2 V2 alpha n Vn. This is a vector in V, and suppose this is 0 here. But all of them should not be 0, because if all of them are 0, this is trivially true. So this is said to be linearly dependent over F if there exists alpha 1, alpha 2, alpha n in F, but not all of them 0. So such that not all of these are 0, and their linear combination is 0. In that case, we say they are linearly dependent. If that is not the case, then we say linearly independent. So, for example, let us take this say V1, A1, 0, 0, and V2, let us take this 2, 0, 0. Then 2V1 minus V2, so plus minus 1 V2, this is 0. Now the scalars, so alpha 1 here is 2, alpha 2 is minus 1. So alpha 1, alpha 2 are not simultaneously 0, but their linear combination is 0. So this implies that V1 and V2 are linearly dependent. The vectors which are not linearly dependent are said to be linearly independent. If the vectors say V1, V2, Vn are not linearly dependent, then they are called linearly independent. So in other words, linearly independent will mean that whenever there is a linear combination, now obviously that you have V1, V2, Vn and they are not 0. None of them is 0. So if V1, V2 say Vn are linearly independent, then none of them can be 0. Because if say some Vi is 0, then you can take the coefficient of this Vi, say alpha I, which is not 0. Any linear combination of these vectors V1, V2, Vn, choosing all coefficients of the j's other than j equal to I as 0, and for this any non-zero will give you a 0 linear combination. So no if V1, V2, Vn in V over F are linearly independent, then none of Vi's is 0 vector. For if say Vi is 0, then say alpha 1 V1, alpha I minus 1 Vi minus 1 plus alpha I Vi plus alpha I plus 1 Vi plus 1 and alpha n Vn is 0, where you can take alpha 1, alpha 2 all here, alpha I minus 1, alpha I plus 1 and alpha n to be 0 for every alpha I not 0. The linear combination is 0. We'll make V1, V2, Vn to be linearly dependent. So none of these Vi's can be 0 if the vectors are linearly independent. Now it is easy to see that some vectors are linearly independent or dependent sometimes just by observation. For example, here We had seen already that 100 and 200 they are let me see there. Let us take say R3. Let us take V to be R3 over R, and S to be the set which consists of say V1 to V equal to let us take V1 to V 1 0 0, V2 to V 0 1 0, V3 to V 0 0 1. Then this is a subset here in V, and the linear span is the whole of V. These vectors V1, V2, V3 V1, V2, V3 are linearly independent. While you can also see that, but you can also take, say, for example, V1, V2, V3, and V4, where V4 is equal to 1, 1, 1, are linearly independent. Says V4, V1 plus V2 plus V3 plus 4 is 0. Vectors, you can take vectors U1 is same as 1 0 0, U2 say 1 1 0, U3 say 1 1 1. So these vectors, if you take, then they are linearly independent. So we have defined the vectors, say V1, V2, Vn to be linearly dependent. If there exist scalars, say alpha 1, alpha 2, alpha n in F, and not all of these scalars are 0, but their linear combination is 0. In that case, we say the vectors are linearly dependent. The vectors say U1, U2, Um are said to be linearly independent if such a thing does not happen. That means they are linear, they are not linearly dependent. Or in other words, or equivalently, you can say that the vectors V1, V2, Vn in V over F are linearly independent if and only if whenever there is a linear combination, say alpha IVI, I1 to N is 0, this implies each alpha I is 0 for every I 1 to N. So they are linearly independent if and only if every linear combination which is 0 implies that each coefficient, the scalar, is 0. We also all when say this representation, two representations are said to be same if the coefficients are exactly same. Otherwise, they are different linear combinations. So let us take say V1, V2, Vn, B vectors in a vector space V over F. Two linear combinations. Two linear combinations. Let us take this say alpha I, Vi, I12, and say beta J, Vj, J12, and now these two are elements in V. Are said to be equal or same if each alpha I is same as beta I for I12. So we say the two linear combinations are same or equal if the coefficient of each Vi is same. The representation is said to be unique. That means if there are two representations, then they are always same. Now, in case of the vectors being linearly independent, then every element in their span is having a unique representation, which is actually a linear combination. So you can see as follows. So let us take that V over F be a vector space. If the vectors say V1, V2, Vn in Vf are linearly independent, then every V in their linear span has a unique representation of the form V is equal to alpha I, Vi, I12, and alpha i's are from F. So for every V in their linear span, there is a unique linear combination which represents the vector V. And the proof is also straightforward, simple. So if you want to prove, so every element in LS is a linear combination naturally. Or if V belongs to the linear span, then there exist scalars alpha 1, alpha 2, alpha n in F, because LS consists of the linear combinations of vectors from S. So suppose you write this element here V in LS. That means there will be scalars alpha 1, alpha 2, alpha n, such that this V can be written as their linear combination. That means this is alpha I Vi. I is equal to 1 to n. We are assuming that the vectors are linearly independent, and we want to show that this linear combination is unique. Presentation is already shown, and that is by virtue of its being the linear span. Now, such a linear combination is unique. Such a linear combination is unique for if there is some other linear combination. Let us take beta j, bj, j is equal to 1 to n, is also a representation of V in V. Then these two linear combinations becomes equal. Alpha ivi, I is equal to 1 to n, is same as beta j, bj, j is equal to 1 to n, will force that each alpha I is equal to beta I, because that is how we have defined the linear combinations. Why so? Since a linear combination alpha ivi is equal to your equal to, let us take say beta j is equal to 1 to n, so this is also 1 to n, and vj. So that means that we have a linear combination here, alpha I minus beta I, I equal to n of the vectors vi's. Since vi's are linearly independent, we get each alpha I minus beta I is equal to 0, or that each alpha I is equal to each beta I. So that makes that the linear combination is unique. So if they are linearly independent, then this representation of the vectors in LS is unique. Now another interesting property which will be repeatedly used but is easy to prove is the following, that if you have vectors say v1, v2, vn, then either they will be linearly independent, and if they are not linearly independent, then so we can prove that next, let us say V or F is a vector space. And V1, V2, Vn in V are vectors. Then either they are linearly independent or they are linearly dependent. Cannot be both. So if they are linearly dependent, if these are linearly dependent, in that case, some Vk is always a linear combination of its preceding ones. Then some Vk, the vector Vk from this list, is of the form that Vk is a linear combination of alpha I, Vi, I is equal to 1 to k minus 1. So either they are linearly independent. If they are not linearly independent, in case of their being linearly dependent, there is a vector, some vector vk, which is actually a linear combination of the preceding vectors, namely v1, v2, vk minus 1, and is easy to prove. So for this we can see as follows. So suppose the vectors are linearly dependent, because if the vectors are linearly independent, then we don't have to do. So in case v1, v2, vn are linearly dependent, then what will happen? There is a linear combination. There exist scalars, say alpha 1, alpha 2, alpha n in F, such that not all of alpha 1, alpha 2, alpha n are 0, but their linear combination is 0. So alpha 1, v1, alpha 2, v2, and 1, alpha n, vn is 0. So all of them are not 0. At least that means there is one which is not 0. Now among the non-zeros, you can take that k is the largest integer for which alpha k is not 0. So you can choose, therefore, choose the largest integer k in this list 1 to n, the largest integer k, which is here, such that alpha k is not 0. That means alpha k plus 1 is 0, alpha k plus 2 is 0. That means alpha k plus 1, alpha k plus 2, all of them alpha n after that are 0. So effectively the linear combination reduces to. So, but then this linear combination becomes what? Alpha 1 v1, alpha 2 v2, alpha k vk is 0, and what we know here is that alpha k is not 0. This is the largest integer k, so that alpha k is not 0. So all other since higher coefficients, this alpha k plus 1, alpha k plus 2, alpha n are 0. So effectively the linear combination is equal to 0, means this linear combination alpha 1 v1 plus alpha 2 v2 plus alpha k vk, alpha k vk, this is 0. And this obviously means that you can write this vk as a linear combination here of v1, v2, vk minus 1, and the coefficient of this v1 will be your minus alpha k inverse alpha 1 v1 minus alpha k inverse alpha k minus 1 vk minus 1. Now this alpha k not 0 will mean that alpha k inverse exists. As this is a field, and field every non-zero element is inverted. So what we have got is that vk can be expressed as a linear combination of preceding vectors, namely v1, v2, vk minus 1. Finally, for you to observe this simple thing, and that can be used, in fact, repeatedly, this observation that if there is a set of vectors v1, v2, vn, then either this is linearly independent or there is some k such that some vk is a linear combination of the preceding ones. So we shall wind up here and we'll meet tomorrow and can obtain some conclusions from this observation which we have proved just now. So thank you very much.
Good morning, sir.
Hello, sir.
Hello.
Sir, there is a student, they wished he wants to, he has some problem regarding course drop and add, so he wants to say something.
Course.
Sir, I am a BTech fourth year student. I tried to enroll in the course, but while adding the course was not coming in the list of the courses which we can add.
So you are not able to add. That's what you are saying.
Yes, sir.
Okay. So what do you want us to do?
Sir, I actually mailed in the student general request. They sent this forwarded the query to you. So I thought that it will be better to inform you about that.
Acha. So that means so there is some mail to me that so and so has requested to add the course for
Uh,
approval.
yes, sir. Most probably it will be like that.